This is Mike Biel. We're going to go over lab exercise 3, high temperature calibration of a strain gauge. In this experiment, we will have 4 different bars, 1 brass, 1 steel, and 2 aluminum. Each bar will have one of these 2 strain gauges applied to it. Only 1 bar will have the correct strain gauge or appropriate strain gauge applied. So here on the left we have a 06 STC series gauge, which is appropriate for steel, and on the right we have a 13 series, which is appropriate for aluminum. Otherwise, the gauges are the same. They're both 120 ohm. They have the same grid pattern and the same grid size. First, just like in lab exercise 1, we'll need to apply the strain gauges. So we'll go through the usual steps: cleaning, surface preparation, so removing surface defects, and then some more cleaning after the abrasion process, followed by conditioning of the surface using Vichy Conditioner A. Conditioner A should be applied in a few steps, 2 or 3 times, never allowing it to dry. And when removing it, you should wipe from the gauge site and out. Here are the specimens after their initial cleaning. They're now ready for application of the alignment marks. So we'll need a few tools for that. For steel, a ballpoint pen works better than an HB pencil or 4H pencil, but the pencil does work nice for aluminum and brass. After the alignment marks are burnished, one final conditioning is required using a Q-tip applicator to scrub, and there will be some burnish mark left after the conditioning yet, so they will be visible. Then neutralizer is applied, and it's agitated into the surface with a Q-tip applicator, and then it is wiped away in the same fashion you remove the conditioner A, starting at the gauge site and wiping outwards. Next, the strain gauges are applied to a clean piece of glass. They are placed face down, and in this case we are going to use solder tabs and some angel hair wires to provide strain relief to the small strain gauge grid. And then our main lead wire will attach to the separate solder tabs. Then these items are placed under the tape, and then they are placed on the test article and aligned. Because they are small, they are the 62/62,000th of an inch grid size. Microscope was used to get the alignment correct, and then they are bonded using M-bond 200 in the catalyst C. And here's our 4 samples with the gauges and solder tabs bonded. And now the samples are labeled. Next, we will protect the strain gauge grid. It's an unprotected grid, so we'll put some masking tape over it. That will prevent any splash from the soldering operation from damaging the grid of the strain gauge. We'll use this 30 gauge angel hair lead wire 570 solder was used for this. It was learned the hard way that solder is difficult to work with. I prefer a lower melting temperature solder. Okay, here are the short angel hair wires installed, bridging from the grid to the solder tab. After that soldering operation, the resistance at the solder tab is checked. And here are the samples with the angel hair wires installed. Next, M code A is applied over the strain gauge and over the angel hair wires. So that will provide some strain relief on the angel hair wires. Several coats of M code A were applied, about 3 to 4. Then 24 inches of 30 gauge 3 conductor cable was cut for each of the specimens. Then that lead wire was soldered to the solder tabs in a 3-wire configuration, and after soldering it was checked with the multimeter. Next, Hypertronics connectors will be installed to the lead wires. So here we're using a pin crimp tool instead of soldering the pins on. Then I am installing the Hypertronics connector. And every bar had a surface mount K-type thermocouple installed as well. Here's the measurement setup. I'm using an LMS Scatus 305 front end. It has a PQBA 4-channel bridge amplifier card in it, and it also has a PQFA card in it, which is a 4-channel general purpose measurement card. I have a thermocouple signal conditioner that's measuring the 4 thermocouples from each bar, and then that signal is going into LMS. So I'm recording the strain and the thermocouple data simultaneously. I'm using TestLab 13A SL2 software for the data acquisition. The signals were measured at the lowest sample rate possible of 64 Hertz. Here's the 4 samples placed in the oven. They're all placed with the gauges facing upward. That way they're not facing the heating element. And there's space in between them so they can each get convection heating around all surfaces. A tie strap was applied at the midpoint of the lead wires at the 12-inch mark. And then when the oven door was shut, the same amount of lead wire for each sample was inside the oven. So inside TestLab, a 3-wire quarter bridge DC circuit is selected, and for this 120 ohm strain gauge, a 3.3 volt excitation voltage is used. Then inside TestLab, the Wheatstone bridge is balanced for all 4 channels. And then using a current injection method, all 4 channels are calibrated to get the calibrated strain. So to get the appropriate millivolt per volt per unit strain. Then the oven was heated up to about 160 Celsius. The test was stopped once the bars got to about 145 Celsius. I ran the test this high because I was interested in seeing the strain error up to a maximum typical engine oil temperature. And so we can see the results here. And then here we can see the results of the difference between a 2 and 3 wire setup. And this was run for bar 1, which has the correct strain gauge applied to the aluminum bar. So blue is the 2 wire, blue is the 3 wire, red is the 2 wire. So you can see there's significant thermal induced error by heating up the lead wires that are inside the oven when using a 2 wire.